This video provides a computational walkthrough on resonant driving in the time-dependent Schrödinger equation, focusing on uncovering hidden quantum dynamics in a square-well system. The core question is how a resonant time-dependent perturbation affects a quantum particle initially in the ground state of an infinite potential well, specifically targeting the transition to the n=3 state. We begin by establishing the unperturbed infinite potential well. System parameters are set to m=1, l=1, and h⁻=1. The initial condition places the particle in the unperturbed ground state, pos ix, 0. Next, we introduce the time-dependent perturbation, v of x, t, which is a product of an amplitude, a temporal driver, and a spatial envelope. We set the perturbation strength v0 to 0.5. The target transition is from the ground state, n=1, to the next symmetric state, n=3. Due to the symmetric perturbation, transitions to asymmetric states like n=2 are forbidden. The resonant driving frequency is calculated as omega equals E3-E1. The particle's evolution is governed by the time-dependent Schrödinger equation, which involves a static core and the dynamic driver, the perturbation. This equation presents an analytical challenge. To solve this computationally, we discretize space and time using the Crank-Nicolson method. This translates continuous physics into a discrete grid for numerical integration, ensuring probability is conserved. The computational grid and timing are configured with a spatial grid of 1,000 points, a time step of 10 to the power of -4, and a total simulation time of 10 driving periods. Our first observable is the spatial probability density, which visualizes the likelihood of finding the particle at any position x at a given time step. Observable 2 is the expectation value of position, which measures the macroscopic center of mass of the quantum state as it evolves. Our third observable is the state populations, specifically P1 and P3. This reveals exactly how much the wave function belongs to the ground state versus the excited state. Executing the simulation for 10 driving periods reveals conflicting narratives depending on the observable. The average position remains constant, while the state populations oscillate. The constant average position is an illusion. Because both the well and the resonant perturbation are symmetric, the probability density expands and contracts symmetrically, causing the mathematical center to remain static. The state populations, however, reveal the quantum resonance. The clear Rabi oscillations between P1 and P3 show energy is being absorbed and emitted, confirming the transition between the n=1 and n=3 states. The physical insight here relies entirely on the chosen observable. To understand a quantum system, you must align your observables with the symmetries and dimensions of the perturbation, as the wrong metric can mask complex internal dynamics. This video explores simulating quantum resonance using a Crank-Nicolson approach to drive the one-dimensional infinite well. We initialize a particle in the ground state of the 1D well. We then apply a resonant perturbation, setting v0 to 0.5 to target the 1 to 3 transition, where resonance requires omega to equal E3 minus E1. Our simulation architecture follows a roadmap from continuous physics to discrete dynamics. This involves defining parameters, discretizing space and time, initializing the wave function, and applying the Crank-Nicolson evolution. The mathematical boundary conditions require the wave function to be 0 at the edges. Computationally, we drop the boundaries by evolving only the interior points, ensuring a cleaner enforcement of boundary values. The continuous state formulation uses the standard infinite well eigenstates. The discrete code implementation explicitly casts the NumPy arrays to complex, which is mandatory for quantum mechanics simulations. The continuous second derivative operator for kinetic energy is approximated by a discrete tridiagonal matrix. We leverage the sparse advantage of the SciPy library for efficient handling of the mostly zero Hamiltonian matrix. The total Hamiltonian is the sum of the kinetic operator T and the diagonal potential operator V. We use the midpoint time for the Crank-Nicolson method because the time-dependent potential requires evaluating the potential at the exact halfway point for better accuracy. The time-dependent oscillating potential is applied. It is evaluated at the midpoint of each time step to maintain second-order accuracy and converted into a sparse diagonal matrix at every iteration. The Crank-Nicolson time evolution is implicitly solved using A psi n+1 equals B psi n. The next state is found by solving a sparse linear system, which guarantees numerical stability. The Crank-Nicolson method guarantees unitarity, ensuring unconditional stability and total particle probability conservation, unlike explicit methods that can diverge. To solve the implicit linear system, matrices A and B are constructed using the identity and midpoint Hamiltonian. We use SP-solve to efficiently compute the next state vector without inverting the large, sparse matrix A. We extract observables at every time step using the store_observables function. This includes density, position expectation value, and population tracking for the n=1 and n=3 eigenstates. Core observables tracked are probability density, expectation value, ground state population, and third state population. The wave function is rebuilt and renormalized before measurements to ensure accuracy. The spatial distribution of the particle expands and shifts outward from the initial ground state peak as the resonant drive injects energy into the system. The expectation value of position remains close to the center due to the perfect symmetry of the setup. To prove resonance, we must analyze the evolving energy state populations instead. This graph is the proof of resonance. By tuning the driving frequency omega to equal E3 minus E1, we see the explicit, successful population transfer from the ground state, n=1, directly into the third stationary state, n=3. This global dynamics map compresses the full spatio-temporal evolution of probability density into a single frame. The vertical axis shows driving time, revealing the wave packet oscillation intensifying as it absorbs resonant energy. Evolving only the interior spatial points and using sparse matrices ensures strict physical boundaries and high performance. The implicit Crank-Nicolson method guarantees mathematical stability over long resonant driving periods.